Oh, it's nice to meet you. Hi, I'm Ryan Kim from Kroma team, and it's very pleasure to be here with our view in Bangkok. Today, I present about what we work on Tachyon, which is a modular ZK backend designed for high performance, accelerated by CPU. And in this session, I'll walk you through what makes Tachyon unique and how we address the key challenges in ZK proof system. And we look at the benchmarks that showcase the Tachyon's capabilities and explore its applications in privacy and validation, and discuss some of the innovative techniques we are using to make ZK proof system more powerful and accessible. And so first, let's take a look at what we've achieved so far with Tachyon. Kroma is the first to implement to ZK for proof, setting a new standard in network security. And we launched as a fully permissionless, meaning that anyone in the network, anyone in the community can participate in the network to help protect assets. There's no special access required, just a bond. Then ask the question, then why is keeping the bond requirement low so important? Let's imagine that if you want to join the network, but were met with high upfront cost, that could be discouraging, right? So by lowering bond requirement low, is make it easy for network participant to participate in network more easily. And we actually optimized the scroll hair 2, and we achieved approximately 1.6 times faster than scroll hair 2 for TX and EVM and super circuit. And with this optimization, we had our moment when Kroma faced its first challenge in April, and thanks to ZK for proof, we can catch and block this long output submission. Let's break down the cost that involved in challenge. Here's how it works. A validator first begins by posting a state loop based on 1,800 blocks. And if the challenger thinks that this state transition is incorrect, they can step in and initiate challenge. Oh, sorry about that. I didn't know that I blocked the screen. And the process uses a create challenge transaction along with 3 bisect transactions. They can narrow down a disagreement to a single block. And then at the final stage, the challenger submit a ZK for proof. But thanks to the optimization we have made, we have been able to cut the cost of proof generation in half, from $20 to $10. What this allows us to lower the bonding requirements to make it easier for many validators to participate in the network. We are using Scroll ZK EVM for this protocol, but this presents the following issues. From a maintenance perspective, we need to keep the ZK tree, which is derived from Scroll ZK EVM, on top of OPGAF. And in the circuit side, we need to follow the optimism derivation logic in the circuit side. Additionally, Poseidon lacks a precompiled OP code, unlike Ketchup, which makes the withdrawal cost via ZK tree more expensive. Also, Poseidon is natively slower than Ketchup. In addition, ZK tree implementation, unlike MPT, Mercury Patricia tree, is inefficient. For instance, any node modification requires recomputing the entire tree hash and writing into disk, which makes it very inefficient, considering the fact that ZK tree is only produced when challenge happens. So to address this issues, we are trying to establish ZK-VM-based fault-proof system using Kona from Optimism, using SP1 from Succinct team. With this shift, our maintenance focus on Kona rather than ZK-VM circuit, and SP1 will replace Layer 2 as a proving backend, and MPT will replace ZK3 as for a state management. And proof generation will shift from local proof generation to SP1 proving service. Let's break down the cost. With this SP1 proving service, overall costs remain almost the same, but now the proof generation costs about $20 to $40 as illustrated. With SP1 and Kona brings us both advantage and disadvantage. Working with Kona reduced the maintenance cost and facilitate the support for multiple ZK VM by using the same gas program. But now we have a dependency on an SP1 proving service so that the validator needs to register with SP1 proving service. But Tachyon is designed to support multiple ZK VM. So if Tachyon were able to operate by anyone, then any desired gas program could generate program through across the multiple ZK VMs through the single backend, which supports efficient use cases. And Tachyon now also has integrated Prongit 3's 235 PCS, which achieves approximately 1.6 times faster than original Prongit 3. And this benchmark is publicly available on the GitHub. So for anyone to test and verify, you can go to check out the GitHub and run the command, and you will show this kind of plot. And Tachyon also is expanding its capabilities to private space, given that a Circum is widely used development tool for privacy preserving applications. So we now integrate support for it. Also, in privacy application, proofs often need to be generated in a limited environment, such as mobile phone or web browser. In this case, the proof generation can become slower or even impossible due to its low memory specification. And this graph extract from MoPro benchmark shows that Tachyon outperforms RapidSnark in SHA-256 circuit and Ketchup-256 and RS circuit by 1.1 to 1.4 times. And also, a member from MoPro team also has reported that for highly complex circuit, Tachyon uses around 40 to 60% less memory. There's more. For those who are familiar with Circum proof generation, before proof generation, the file called witness file should be generated before proof generation. And this witness file could be generated by using C++ step as shown in blue and purple step, or wasn't as shown in red and purple step. In production, typically C++ is preferred due to its speed, but in case of ZK email, their circuit is so large and the C++ file contains millions of lines, so compiling this file can take up to 6 hours and leading to out-of-memory issues. But we fixed the problem and devised a way to split this one large single file to split to several small files and pairwise the compilation time so that we can reduce just 10 minutes. Now, let's analyze SP1 proof generation. The green box on our left side represents commit operation, and the blue box on the right side is open operation. And I forgot to say, and this profile result represents the Fibonacci proof generation using SP1, and as expected, combit operations has significantly larger portion than open. And let's take a closer look at the pink highlighted section, which represents create first digest layer function. This image shows a result of using static method to pairize the pink highlight in pink, where the tasks are chunked and assigned to CPU in a predetermined order. As you can see that some CPU finish tasks early, but others takes longer. We can improve this performance by using dynamic pairizations by allowing CPU to put chunks as they become available. Yeah, this achieves 20% speed boost, but we don't think that it doesn't really solve all the scheduling issue. So let's explore what the create first digest layer function does. Imagine there's a table where a column is a polynomial and row is an evaluation point. What this function does is generate hashes from the evaluation results for each polynomial using Poseidon2 hash function. After creating a first digest layer, the additional layers are built similarly. And to create a next digest layer, it needs to combine left and right child value from the previous layer. In the end, it creates a tree as shown. But the issue is that the degree and number of polynomials are very large, leading to high memory usage or cache misses. So as you can see that in order to create a digest loop, the elements in the digest 2, you don't need all the elements in the previous layer, which means if we had information on device capabilities and the cost of each calculation, we can make faster. Now let's analyze the time taken for second proof generation. Because of time limitation, I will make it faster. I proceed faster. So FFT and MSM will dominate the time. And our MSM entity are already faster than existing libraries. MSM is 1.8 faster than ArcWorks. With iSQL integration, we can achieve 10 times faster. Yeah! And entity, ours faster than 1.4 times faster than ArcWorks. With iSQL, 4.5 times faster. And all these benchmarks can be rerunnable on GitHub. And as you can see in the second proof generation, I skipped some details, but you can see that there's a white. So on the right side, it represents MSM, and white space indicate a CPU downtime with an arrow pointing to 2.8 seconds. It's a downtime quite significantly in 16.9 seconds total for MSM. If you analyze the downtime ratio, for all these MSM, each thread roughly 30% downtime in average. Which means, so the reason for this is because the unit of pairization is big. For instance, if you have an MSM of size 16, and if you have divide this MSM into 4 CPU, and this leads to this kind of graph. And as you can see, some CPU, so the time to complete each task varies, leading to this downtime. So this implies that for optimal performance, scheduling is very important. The same applies to entity. This image represents the process of entity for polynomial of size 8. As you can see that the entity process goes more complex with each stage, which makes it very complicated for pairization. And currently, iSQL needs the whole required data, which consists of input and output polynomial and tweeters to be fully loaded to memory. So some certain circuit might even not generate a proof even with a high-end device like RTX 4090. But I just heard from the owner that this will be fixed in 3.1 next version in Isker. So yeah, we are looking forward to the clever solution so that we can integrate this Isker to Tachyon. So in conclusion, Tachyon supports faster Layer 2 and SP1 generation for permissionless validator system. And Tachyon supports faster and memory-efficient circumproof generation for privacy-preserving applications. And as you can see in the analysis, for optimal performance, the scheduling should be fixed in a clever way. And now we are designing a new version of Tachyon to maximize the device utilization ratio so that we can make use of the multiple device in an efficient way. Yeah, that's all. Thank you.
Thank you, Ryan. What an exciting opening. Thanks for sharing the magic numbers. So, any questions for Ryan? Sorry? Oh, check out Ingonyama YouTube. We'll upload the video. Yeah. Okay, thank you, Ryan.
I have a question.
Okay,
Hi,
please.
Ryan. Great talk. Can you give us an idea of how much memory does a prover need? So, like, kind of, so, for example, like a physical machine. So, in terms of number of gigabytes.
The question was how much memory was needed for some certain operation and
yeah. So, for example, when you said you needed a lot of memory, so you ran into memory issues when.
Okay. In case of SP1, they use degree of 2 to the 27, and for circum case, I don't remember exactly the degree, but I can share right after I check out the number. But it was about the Plonky2 verification logic in circum, and I was given from Orbital Finance team.
Okay, thank you.
Thank you. Thank you, Ryan.